Hello, welcome to another module in this massive open online course on estimation, MMSE estimation for wireless communication systems. Alright, and what we are looking at currently is the MMSE estimate of the parameter in a wireless sensor network, and we have derived the expression for the MMSE estimate as H hat, that is the MMSE estimate of the parameter H hat at the fusion center is, well, that is 1 bar sigma h square times sigma h square into 1 bar transpose plus sigma square I inverse into y bar minus 1 bar times mu h plus mu of h, okay. And this is basically, remember we said this is basically the expression for R h y, and this is basically R y y inverse, okay, where R y y is sigma h square 1 bar transpose plus sigma square times the identity matrix, okay. What is this? This is the MMSE estimate of the MMSE estimate of the parameter h of parameter h in the WSN or in the wireless sensor network. Now, what we are going to do in today's module is to further simplify this expression for the estimate of the parameter h. Alright, so this is a complicated expression, so we are going to further simplify it, right, so that it's more easier to interpret and more easier to draw inferences from. So what we are going to do is to basically simplify this expression, and to simplify this expression, note the following thing. First, let us start with this quantity over here, okay. Let us start with this quantity, that is sigma h square 1 bar, there is 1 bar transpose, 1 bar transpose plus sigma square into 1 bar transpose. Now, I can look at this quantity, I can simplify this into two forms, right. First, what I can do is I can take 1 bar transpose out on the left, and then this becomes 1 bar transpose sigma h square into, or 1 bar transpose times sigma h square 1 bar transpose plus sigma square times identity. This is the expression I get by taking 1 bar transpose common on the left. Now, what I am going to do is I am going to take 1 bar transpose outside on the right, and then what I get is sigma h square 1 bar transpose 1 bar plus sigma square times 1 bar transpose. This is by taking 1 bar, let me just write it down, by taking 1 bar transpose common on the left side, by taking 1 bar transpose common on the right side, okay. So the same expression we have simplified it two different ways, that is by taking 1 bar transpose common on the left hand side and 1 bar transpose common on the right hand side, alright. And therefore, these two quantities are basically one and the same, and therefore, these two quantities are equal. So what we have is, let me write it down, 1 bar transpose sigma h square 1 bar transpose plus sigma square times identity is essentially equal to sigma square 1 bar transpose into 1 bar plus sigma square into 1 bar transpose. And therefore, now what I can get is I can take the inverse and multiply this on the right. Okay, here inverse and multiply on right of the expression on LS, and this term I can bring it over here, take the inverse and multiply it on the left, that is take inverse and multiply on the left, and when I do that I can now simplify this interestingly as sigma h square 1 bar, right. What do I have? I have sigma h square 1 bar transpose 1 bar plus sigma square inverse into 1 bar transpose. This is equal to, well, this is equal to 1 bar transpose into sigma h square 1 bar transpose plus sigma square identity inverse. Okay. All right. Now, what I am going to do is I am going to multiply both sides by the scalar quantity sigma h square. I am going to multiply LHS and RHS by the scalar quantity sigma h square, which is the prior variance of the parameter h, and of course, the equality remains unchanged because this equality holds because you are multiplying LHS and RHS by sigma h square. So, multiply both sides and it is a scalar quantity. So, I can place it appropriately anywhere. So, sigma h square 1 bar transpose 1 bar plus sigma square times 1 bar transpose equals, and I am multiplying by sigma h square. So, I can just insert the sigma h square over here, sigma h square into 1 bar transpose. This is equal to the RHS, which is sigma h square 1 bar transpose sigma h square 1 bar transpose plus sigma square identity inverse. Okay. Now, observe this quantity 1 bar transpose 1. Now, observe that this quantity 1 bar transpose 1 bar is simply, what is this? This is the row vector, the n dimensional row vector of all ones times the n dimensional column vector of all ones, which is simply equal to n. 1 bar transpose 1 bar is equal to n, and therefore, what we have now is, interestingly, this quantity here, this is basically sigma h square into n plus, it is a scalar quantity, you can observe that sigma h square n plus sigma square into 1 sigma square inverse into sigma h square 1 bar transpose equals sigma h square 1 bar transpose sigma h square 1 bar transpose plus sigma h square identity inverse. Now, this is a scalar quantity, look at this, this is simply a scalar quantity. So, the inverse is the reciprocal. So, this is a scalar quantity. And therefore, we have sigma h square divided by sigma h square n plus sigma square, which is equal to sigma h square 1 bar transpose sigma h square 1 bar transpose plus sigma h square identity inverse. And now, if you observe the quantity on the right hand side, let us say this quantity, let us denote this by star. this quantity is the same as, if you look at this quantity is the same as this quantity. Observe that this is the star quantity which is simplified below. Right, and therefore, now if you look at this, now I can replace this and now I can simplify the expression. So, in the earlier expression for h hat, I can replace the star quantity by our simplified expression here, and now the MMSE estimate for h hat can therefore be derived as sigma h square 1 bar transpose divided by sigma h square n plus sigma square times y bar minus 1 bar mu h plus mu h. Okay. So, this is after substitution. Okay. And therefore, now look at this, I have sigma h square 1 bar transpose into y bar. So, that becomes sigma h square 1 bar transpose into y bar divided by sigma h square n plus sigma square minus sigma h square 1 bar transpose 1 bar. Look at this, sigma h square 1 bar transpose 1 bar, that is n. So, this is sigma h square 1 bar transpose 1 bar, which is n times mu h divided by sigma square n plus sigma square. In fact, this should be sigma h square in the denominator. So, this is sigma h square, sigma h square, sigma h square plus of course mu h. And now, if you look at this, the term on the right, if you look at this, I have sigma h square n mu h minus sigma h square n mu h plus mu h n sigma square. So, what I will get if I simplify this is basically sigma h square 1 bar transpose y bar divided by sigma h square n plus sigma square plus sigma square mu h divided by sigma h square n plus sigma square, which is equal to, therefore, this is equal to sigma h square 1 bar transpose y bar plus sigma square mu h divided by sigma h square n plus sigma square. This is the simplified expression. So, this is the simplified expression. It is a much simpler form because it does not involve any matrix inverses like we have seen simplified expression, and we are going to simplify it further, but this is a sort of an intermediate simplified expression of the MMSE estimate. Alright. And now I am just going to put it in the form, in a slightly improved form, a slightly more intuitive form. What I am going to do is I am going to divide numerator and denominator by sigma h square sigma square. So, divide numerator comma denominator by sigma h square by the product sigma h square sigma square. What that will give me is 1 bar transpose y bar divided by 1 bar transpose y bar divided by sigma square plus mu h divided by sigma h square divided by 1 or divide n divided by sigma square plus 1 divided by sigma h square. I am going to now write this in a slightly more convenient form. I am going to 1 bar transpose y bar divided by n divided by sigma square divided by n plus mu h divided by sigma h square divided by 1 divided by sigma square divided by n, just a slightly different way of writing it, by 1 divided by sigma h square. Now, look at this, this is an interesting, this has a very interesting interpretation. Let us look at this term by term. What is this quantity 1 bar transpose y bar divided by n? Let us dissect this expression. What is this quantity 1 bar transpose y bar divided by n? Now you will realize that is something very interesting. 1 bar transpose y bar divided by n this is equal to 1 row vector of all ones times y1 y2 up to yn 1 divided by n, which is nothing but, if you look at this is a very interesting interpretation. This is summation 1 over n equal to 1 to n y of n, and then if you look at this is nothing but the average of the samples. This is a sample mean, and this is also basically the maximum likelihood estimate, right. This is also, if you remember, some people who have done the previous course might remember, this is the maximum likelihood or. So the first component 1 bar transpose y bar divided by n, which is nothing but 1 over n summation n equal to 1 to capital N y of n, is basically the average of the observations. This is known as the sample mean. This is also the maximum likelihood estimate. Okay. And now let us look at this sigma square divided by n in the numerator. This is nothing but the variance of the maximum likelihood estimate, sigma square divided by n. This is equal to the variance of the ML estimate. Now you look at this mu h is the mean of the prior and this is the variance of that is the mean. Mu h is the mean of the prior. Remember we said the parameter h is Gaussian with mean mu h and variance sigma h square. So the mean of the prior is mu h, variance of the prior is sigma h square. Therefore you have a very interesting interpretation for this. So h hat equals, what does it equal to? It equals the ML estimate divided by ML variance plus prior mean divided by prior variance divided by 1 by ML variance plus 1 by so it has a very beautiful interpretation. What it is doing is basically we have the ML estimate, the maximum likelihood estimate, and you have the prior mean, that is mu h, that can be treated as another estimate of the parameter h, and then you combining or you are performing a weighted combination of these two estimates, the ML estimate and the prior mean, in the inverse ratio of their variances. That is you are weighting each, that is you are weighing each estimate by the inverse of the variance, because remember if the variance is high the estimate is less reliable. Therefore what you are doing is you are weighting by the inverse of the variance. So if the variance is high, the inverse of the variance is low, therefore the corresponding weight is less. So what you are doing is you are taking these two estimates and combining them in the inverse ratio of their variances, and that is the beautiful interpretation the MMSE estimate has. Alright. So and that is the expression. So therefore the final expression for the MMSE estimate h hat, let us write it down again, the final expression, and this is a very interesting expression. Although it looks initially it looks very complex, it has a very beautiful and a very interesting interpretation. 1 bar transpose y bar divided by n divided by the ML variance plus the prior mean divided by the prior variance divided by inverse of the MLS variance plus inverse of the prior variance. Okay. So it has a very beautiful interpretation, and one has to appreciate this beautiful interpretation of the MMSE estimate in the wireless sensor network. So, this is the MMSE estimate for the wireless sensing network, where the parameter H is being sensed by the wireless sensor network. Okay. All right. So, this is the simplified expression for the MMSE estimate. Let us do a simple example to understand this. Okay. So, simple example for a wireless sensor network. Yeah, let us do a simple example to understand this. Let us consider n equal to 4 measurements or n equal to 4 sensors, which naturally means that there are n equal to 4 measurements. Let the measurements be denoted by, y1 equals 1, y2 equals 2, y3 equals 2 and y4 equals 1. Then the ML estimate, and also let us say the noise variance, dB noise variance, that is sigma square, let us say the dB noise variance sigma square in dB equals, well, this is equal to minus 3 dB, which implies that basically your 10 log 10 sigma square equals minus 3, which implies sigma square equals 10 to the power of minus 3 minus 0.3 equals half. Okay. And therefore, the ML variance, remember the ML variance equals sigma square divided by n, that is half, divided by n equal to 4, that is 1 divided by 8, that is the ML variance. Okay. Sigma square 1 divided by n, half divided sigma square divided by n, that is half divided by 4, that is 1 divided by 8, that is the ML variance. Now, let us look at the prior. Let us say the prior, given prior mean, let us say prior mean given, of course, this information has to be given, mu h equal to 3. What is this? This is your prior mean, and sigma h square equals 1 over 4. This is the prior variance. Okay. And now, therefore, the now let us compute the ML estimate. ML estimate, remember that is what we need, h hat ML. What is this? This is basically your ML estimate, that is simply the sample mean. That is equal to 1 over 4 summation n equal to 1 to capital N, which is 4 of yn, the observations yn, which is basically 1 over 4 times 1 plus 2 plus 2 plus 1, which is equal to, well, that is 6 divided by 4, which is equal to 3 divided by 2. Therefore, the MMSE estimate, alright, we have already seen the ML variance, therefore, MMSE estimate h hat MMSE, let me just write it a little bit more clearly, h hat MMSE equals, now we have all the required quantities, that is the ML estimate divided by the ML variance, that is 1 over 8, plus the prior mean 3 divided by the prior variance, that is sigma h square, which is 1 over 4, plus 1 over the ML variance plus 1 over the prior variance, which is basically equal to 12 plus 12 divided by 12, which is 24 divided by 12, which is equal to 2. Therefore, in this simple example, the MMSE estimate of the parameter H hat MMSE, that is equal to 2, where this is the MMSE. Let me just write that again. This is the Bayesian, this is the Bayesian MMSE Bayesian MMSE estimate of the parameter H. This is the Bayesian MMSE estimate of the parameter H. All right. So, what we have done in this module is we have simplified the expression of the MMSE estimate of the parameter H in the wireless sensor network, and finally, we have also seen a simple example of how to compute this MMSE estimate for a simple scenario with n equal to 4 observations. And what is interesting is we have seen that this MMSE estimate has a very beautiful interpretation. It is the combination of the ML estimate, the classical ML estimate, which is a sample mean, and the prior mean in the inverse ratio. It is a linear combination, a weighted linear combination of them in the inverse ratio of their variances. All right. So, with this module, we will stop here for this module, and we will continue with other aspects in the subsequent modules. Thank you very much.